Hey guys, welcome back to Virtual Physics. This is Ms. Whiteley. Today we're going to be looking at some constant velocity notes. And to start off with, we're going to need to do some vocabulary. So our first two vocabulary words are scalar and vector. And they're pretty similar because they both are a numerical quantity, so simply a number. And how big the number is called the magnitude. Okay, so they both have magnitude because they are both numbers, but one of them has no direction. That's a scalar. Scalar does not have a direction, but vector does. Okay, so some examples here might be like a scalar number is something like the mass of an object. Okay, we could say something has a mass of 5 kilograms. Okay. And mass doesn't have a direction associated with it, it's just straight up a number. It would make no sense to say 5 kilograms up or 5 kilograms to the left. So that number, because it has no direction, is a scalar. But a vector does have directions. So that could be something like the thing we're talking about today, which is velocity. So an object could be going 5 meters per second, and it would make sense to say it was going 5 meters per second to the left, or you could say 5 meters per second to the right or up or down or whatever direction. But the point is, a vector does have a direction associated with it while a scalar doesn't. And I always liked to bring people back to one of my favorite movies of all time, Despicable Me. And in Despicable Me we have a lovely villain named Vector, and Vector has this whole scene where he introduces himself and his name, and he says he's committing crimes with both direction and magnitude, and that is a vector. But scalar, just a number, has no direction. I forgot, we have blanks down here for examples. Scalar, we said the example was mass, and vector, our example was velocity. All right, up next we have the word rate. So rate simply describes how much something changes over time. Today we're going to be looking at speed and velocity as rates because they are how something's position or where it's at changes over time. And the first of those two words that I just said is speed. Okay, so speed is a scalar quantity, and scalar means it has no direction. Okay, so speed just describes how fast something is going, how its motion changes over time, or how its position changes over time, but without a direction. So an example of this could be that you go down I-20 at 70, now it is 70 miles per hour. They recently changed the speed limit, 70 miles per hour. I know that's not our standard metric units, but that's what you drive in is miles per hour. So a speed would be saying 70 miles per hour, but a velocity would be describing that speed in a specific direction because it is a vector. You can think speed, scalar, they both start with an S, velocity, vector, they both start with a V. So a velocity might be that you're headed 70 miles per hour towards Shreveport, which is east. Okay, so now it's got an associated direction, and that makes it a vector. All right, we're going to move on down to the mathematical portion of this. Okay. So when we say something is moving, we've got a rate of motion here for velocity. We mean it is changing position, okay? So say we have a number line. Number line looks like this. And we've got some marks on it that we could label. Okay, like 1, 2, 3, 4, negative, sorry, I was writing the wrong number. Negative 1, negative 2, negative 3. Sorry, it's not symmetrical. It'll be all right. Okay, so we've got a number line, and say we've got an object that starts off at 0 and it moves. Okay, as it moves, its place on the number line is changing. Okay, so it could start at 0 and it can move to negative 1, or it could start at 0 and move to 3, or it could start at negative 3 and move to 4. Okay, the idea of motion is that we are changing position, and velocity is how fast we are changing position and in what direction. So we have a mathematical symbol that represents change. It is a Greek letter delta. Okay, it looks like a triangle. So that's called a delta. and it means change. Anytime you see a delta in physics, it means change. So our change in position is going to be triangle for change, and then if we're moving horizontally, it's going to be an X for position. Like this would be an X-axis on your graph. If we're moving horizontally, we would say change in X for changing position in your X direction. Now, velocity is a rate of change over time. It's how much our position is changing over time. So when you're changing time, you would say delta for change and then t for time. Now, to actually get a velocity, you use both of those things, change in x and change in time, and you divide them. It's how much your x changes per change in time. And that equals velocity. Velocity equals change in x divided by change in time. Now, the way we usually indicate direction with this is just like you would on a number line with positive and negative. So on my number line here, I've got a positive side and a negative side. If my change in x is in the positive direction, so say I move from -2 to 3, that's in the positive direction, so my velocity will end up positive. If I go the other way, go from 1 to -3, my change in x is going to end up being negative, so I'll have a negative velocity. I'm moving in the negative direction. And for these first few problems, we're not really going to pay that much attention to direction. We're just going to work on the calculation aspect of it. But later on down in the notes, we are going to start looking at some directional things. All right, so let's move on down to a question. Now, our questions, we're going to be solving using what's called the I-guess method. And let's read the question first, and then I'll talk you through what the I-guess method is. Our question says, if an unladen swallow can fly 50 meters in 4.6 seconds, what is the airspeed velocity of an unladen swallow? Hopefully someone will get that reference. But anyway, the I-guess method starts with an I, and the I is drawing your scenario, okay? So in this instance, drawing the scenario, not that big of a deal because it's not really that useful. But later on, as our problems get more complex, it will be super helpful, okay? So I'm going to draw my bird here. That's my swallow. Looks kind of crappy. And it's going to fly this way, which is not how it looks in the picture. It goes 50 meters and takes 4.6 seconds. But I'm not going to draw seconds. We just get 50 meters. Okay, so that's my image. That's what's happening. And I'm going to make my bird go to the right. All right, next up we have the G and the U. G stands for givens, and U stands for unknown. So here we're going to write everything we were given in the problem and figure out what it is we're looking for. So the givens usually look like numbers. Sometimes they're hidden in the words, but this time around they all are numbers. And the first number you see here in this question is 50 meters. 50 meters is how far the swallow went. How far the swallow went, we are labeling as a change in position, which is a delta x. That's how far we flew in the x direction. And then the next thing we are given is 4.6 seconds, which is a time, okay? Because seconds measures time. And that's how much the time changed while the bird flew 50 meters. So we've got a delta x, we've got a delta t, and the question asks, what is the velocity? Okay, velocity is the v, so I'm going to put velocity equals question mark, because we do not know. And those are our two givens and our one unknown. Then we get to the rest of the word, ESS. That stands for equation, substitution, and solve, or solution, whichever. And you can just use all of this space. You don't have to go right by each letter. But our equation that we have is delta x divided by delta t equals v. And that is already nice and solved for what we want. We want the v, the equation solved for v, so we don't really have to do any algebra here. We're just going to move straight to substitution, which is plugging in numbers. So for delta x, if we look up to our givens, we see that the delta x is 50 meters. So instead of the delta x, we'll write 50 meters. And then we do the same thing for delta t. Delta t is 4.6 seconds. So instead of delta t, we'll write 4.6 seconds. And that equals velocity. So we'll go ahead and divide those up to get a numerical answer. And when you divide that using a calculator, you do not have to work that one out by hand. You get 10.87. And for a unit on velocity, we look at our equation here, okay? So we divided the 50 and the 4.6, but if you look at the units, you're also going to divide those. And you can't really divide units, but we'll write them as meters over seconds, which is also meters per second. So that unit for velocity actually comes from the math itself. It's not just made up. So we've got 10.87 meters per second is the speed, but to make it a velocity and a vector, we have to give it a direction. For the direction, you can look back over at your picture. And in my picture, I decided we were going right. Since the problem didn't specify, your picture could say left. All right, let's go ahead and look at number 2. Number 2 says if you traveled a constant velocity of 97 kilometers per hour, which is about 60 miles per hour, how many kilometers can you travel in 3.2 hours? So we're going to go ahead and draw an image. It says if I travel this far, or this distance, this speed, this time, whatever. So I'm going to draw a person. I like to make them going right. And we're traveling at a constant 97 kilometers per hour. So I'm just going to write that here on my picture. And it asks how many kilometers can you travel in 3.2 hours. So we're going to go ahead and do our givens and unknown over here, where we write down everything from the problem that we know. So let's go ahead and scan through, look for numbers. The first number I see is 97 kilometers per hour. And kilometers per hour, it says, is a constant velocity. So we're going to make that equal to v. And we don't really need the 60 miles per hour. You could use it to find out how many miles you can travel, but here it's just extra information to give you a little bit of context on what 97 kilometers per hour means. And then it asks, how many kilometers can you travel in 3.2 hours? So 3.2 hours is our second given, and that is a time. So we put change in time with 3.2 hours. And our question asks, how many kilometers can you travel? And kilometers is a unit of distance, so we're going to use delta x for that. That's what we're trying to find, how far we went, which is the delta x. Now we move on down to the ESS. The equation is, as always for this practice, velocity equals delta x divided by delta t. Now in this case, we're looking for delta x, which is not what our equation is solved for. So here you have two options. You can either go ahead and algebraically manipulate it, or you can go ahead and substitute and solve. I'm going to do it both ways here. So if we algebraically manipulate, we're going to solve for delta x. To solve for delta x, we need to get rid of that pesky delta t down there, okay? Delta t is on the bottom, we don't want it anymore. And in order to get something off the bottom of a fraction, which means it's being divided, you have to do the opposite of division. So instead of dividing, you're going to multiply. But what you do to one side, you have to do to the other. So you get delta t times v equals delta x as your new equation. And then you can go ahead and substitute from there. The other option was to take your original v equals delta x over delta t and just straight up substitute before doing any algebra. Okay, so I'm going to show you how that one works. That would be, starting with the v, you go look in your givens and go ahead and plug it in. So do 97 kilometers per hour equals delta x, which we don't know, so we leave it alone, divided by delta t, which we found up here. It's a terrible arrow. And delta t is 3.2 hours. But now we have to do the same algebraic steps, just with numbers instead of letters there. We've got 3.2 hours in the bottom. We don't want it there, so we have to multiply on each side. And when we multiply, those go away, and we end up with 3.2 hours times 97 kilometers per hour equals delta x. And then we just have to type in those numbers to a calculator. And when I type them in, I get 310.4. Now for units on this one, things are a little bit different. We don't have meters and seconds anymore, but we still do the same math with the units. Okay, we've got hours on top here and hours on bottom. And you should know from math that if something is the same on the top and bottom of a fraction, they just cancel out. So the hours go away, and the only part of the unit you end up with left is kilometers. So our constant velocity here is 310.4 kilometers, and with velocity you have to have a direction. My direction in my picture is to the right. Okay, number 3 down here is going to be a little bit more challenging. And it's going to be a little bit more challenging because of the algebra. So what I want you to do is pause this video and work through this problem on your own as best as you can, just number 3. And then once you're stuck or you feel like you're done, you can play this video and I'll work it through and you can see how you did. All right, so for images, we're going to do Usain Bolt, my best stick figure impression of Usain Bolt running. I don't know how someone's arms look while they're running. They probably don't look like that. But okay, so he's running 400 meters to the right, as per usual in my world. Okay, and things that we know are he's running 400 meters. That is his change in position, how far he goes. And at his top speed, 12.422 meters per second. So speed is like velocity minus the direction. And we are looking for how long would it take, which is a delta t. Okay, so we use the same equation, velocity equals delta x over delta t. And if we're going to do the algebra on this one, it's a little bit trickier. Okay, so delta t is in the bottom there, which is disgusting. Solving for things that are on the bottom of fractions is never ideal. So when you're solving for something that's on the bottom of a fraction, you always have to start by multiplying it out of there. Okay, and some people call this cross multiplication. It's basically the same idea. So you're going to take the delta t and multiply by it on both sides to get it out of there. Okay, if you do that, it makes it go away from this side and it ends up in the top over here. And that's the same as if you had just cross multiplied it up over there. So you get a new equation that says delta t times v equals delta x. But it's still not solved for delta t yet because you've got a v over there with it. So you can go ahead and divide by v on both sides, which gets you this equation, delta t equals delta x over v. And you can substitute into that one. You can also go ahead and substitute from the beginning and then solve with the algebra, but the algebra steps are the same. So I'm just going to go ahead and use this equation that I just made and substitute in there. So we get delta t equals delta x, which is 400 meters, divided by 12.422 meters per second. And when I type that into my calculator, I get 32.2. And to look at units on this one, it's a little bit weird. You've got meters divided by meters per second. And you should know with fractions that when you divide by a fraction, you're actually flipping and multiplying. So you do m times seconds divided by meters. But what happens here is that there's a meters on top and a meters on bottom, so they cancel out and go away, and you end up with just seconds, which makes sense because that's the unit for time. So we get 32.2 seconds is Usain Bolt's record for that 400 meters at 12.422 meters per second. All right, number 4 down here is a little bit different, okay? It is not super much calculation. It's more thinking and figuring out stuff with vectors. So the question says the maximum allowed wind assistance for a world record run is 2 meters per second. This is real facts. When runners are running, if the wind is too strong behind them or in front of them, they don't count the times anymore because of the wind assistance. Anyway, if Usain Bolt can run 12.422 meters per second unassisted, that's with no wind, how fast will he run in a headwind of 2 meters per second? And then how fast in a tailwind of 2 meters per second? So let's go ahead and draw this scenario, starting with the headwind. So this is Usain Bolt, and he's going to be running to the right, typical Usain. Okay, he's running to the right, 12.422 meters per second. And the wind, if it is a headwind, means it's coming at his head. Or going the opposite direction that he is. He's running into it, okay? And it's going 2 meters per second. So essentially what happens here is he's trying to run into the wind, and the wind is pushing back against him, okay? So he's going to be running slower than what he would have. And you can see that because one of these is in a positive direction, and one of them is in a negative direction. They're going opposite. So we're going to take those two speeds, or two velocities, those two vectors, and add them together. But when you add them together, one of them, the wind, is in the negative direction, so we make it a negative. So we end up with 12.422 minus 2 equals 10.422 meters per second is how fast Usain Bolt would run into the wind. So essentially we're just taking his top speed and subtracting the wind speed from it. But if we do a tailwind, on the other hand, here's Usain running 12.422 meters per second to the right, which will make positive. And the wind is a tailwind. Tailwind means it's pushing with him. Okay, it's pushing on his tail. And it's going 2 meters per second. Now those are both going in the positive direction. The wind is helping him. It's going to help him go faster. So we take and we add those two together. 12.422 plus 2 equals 14.422 meters per second. So when two speeds are going the same direction, you add them. If they're going opposite directions, you're going to subtract them. And that's when the direction really starts to matter. The vector part starts to matter. All right, so now you've gone through all of the constant velocity notes. Go ahead and go look at your practice in Google Classroom. After you finish your practice, the numerical answers for those questions will be on the assignment. You can go look in the description and it'll have the numerical answers there for you. And so you can check those and then go ahead and take your constant velocity quiz and get that submitted as soon as you can. All right, see y'all later.